Welcome to our latest video on the topic of BornHaber cycles. This video is suitable for A-level students. By the end of this video lesson, you should understand the processes involved in the formation of simple ionic compounds as described in a BornHaber cycle, and you should be able to construct BornHaber cycles from given data and be able to use these cycles to find enthalpy values. Now in this video we're going to focus on Born-Haber cycles, and a Born-Haber cycle is essentially a big Hess's Law diagram, so it's really important you understand the principles of Hess's Law and you can use Hess's Law diagrams to calculate enthalpy values. Now at AS level, one of the most important concepts you would have covered in energetics was Hess's Law. Now Hess's Law, which was formulated in 1840, helps us to calculate enthalpies for chemical reactions. And it states that the enthalpy change is the same for a reaction whether it occurs in one step or a number of steps. So here we have A going to D, and the enthalpy for that, delta H4, is equal to delta H1 plus delta H2 plus delta H3. And that's because the enthalpy change to go from A to D would be the same if I went to A to B to C to D, because it doesn't matter if I go in one step or a number of steps, the enthalpy change is the same. Now an advantage of Hess's Law is that we're able to calculate enthalpy changes without having to carry out the reaction. So if we use this example and we're looking at delta H4, the enthalpy change from A to D, we don't have to carry out that reaction of converting A to D in one step, because we can just work out the enthalpy changes of A going to B and then B going to C and C going to D, and by adding them up we can calculate the delta H4 value, the value from A to D. And this is useful because it might be that the reaction converting A to D might be violent or too dangerous for us to carry out, or it might be over too quickly. So Hess's Law enables us to still find out the value of delta H4 without us having to complete this reaction. So Born-Haber cycles are just an application of Hess's Law, and they can be used to calculate lattice enthalpies. Now by lattice enthalpy we mean lattice break-in enthalpies and the enthalpies of lattice formation. Now lattice enthalpies cannot be determined directly by experiments, but they can be calculated indirectly using Hess's Law and other enthalpy changes that can be found experimentally. Now the energy cycle used to calculate a lattice enthalpy is called a Born-Haber cycle, and the basis of a Born-Haber cycle is the formation of an ionic lattice from its elements. So we're now going to look at the principles of a Born-Haber cycle. So I'm going to use the example of sodium chloride here, an ionic compound which is made up of a metal and a non-metal, to illustrate the different stages in a Born-Haber cycle. So the two elements that make up sodium chloride are sodium and chlorine. And sodium is a solid under standard conditions, and chlorine is a gas. So the first thing I'm going to do now is write an equation to represent the standard enthalpy of formation of sodium chloride. So that would be Na plus half Cl2 goes to NaCl. Now the standard enthalpy change of formation is forming 1 mole of a compound from its elements in their standard states under standard conditions. Now sodium chloride is an ionic compound, so it's made up of billions and billions of positive and negative ions held together in a giant structure called a crystal lattice. And the standard enthalpy change of lattice formation is the enthalpy change that occurs when 1 mole of an ionic compound is formed from ions of the elements in the gas phase. So I can represent this by Na plus gas reacting with Cl minus gas forming NaCl, and that represents the enthalpy of lattice formation. And under standard conditions it would be the standard enthalpy change of lattice formation. Now, to complete my BornHaber cycle, I need to get from Na as a solid and half Cl2 as a gas to Na plus gas and Cl minus gas. And to do this, we need atomization, ionization, and electron affinity. So atomization is where you form 1 mole of gaseous atoms, and the enthalpy change of atomization is the energy change when you form 1 mole of gaseous atoms. So I've written an equation here to represent the atomization of sodium. Now I also need to convert chlorine molecules to chlorine atoms. So I'm writing an equation here to represent the enthalpy change of atomization for chlorine, because I'm forming 1 mole of chlorine atoms. Now, once I've got sodium atoms and chlorine atoms, I need to convert these to Na plus ions and Cl minus ions. So to convert sodium as a gas to Na plus ions, I need to remove an electron, and this is called first ionization energy. So Na is going to Na plus gas plus an electron, and the enthalpy change of ionization here would be the energy change when you convert 1 mole of gaseous atoms to 1 mole of gaseous positive ions by removing 1 mole of electrons. Now, to complete my cycle, I need electron affinity. Now, this is the enthalpy change that occurs when 1 mole of gaseous negative ions are formed from gaseous atoms of a substance by gaining electrons. Now my BornHaber cycle is complete, and at A level we'll be expecting you to use a BornHaber cycle to find out a missing value here, and usually you're expected to find either the lattice forming or breaking enthalpy or the enthalpy of formation. However, you could be asked to find other changes such as atomization or ionization or electron affinity. So here's a BornHaber cycle to represent an ionic compound MX, where M is a metal and X is a nonmetal, and the ionic compound MX is made up of M plus ions and X minus ions. And I've drawn in the various stages and the various energy changes that make up this BornHaber cycle. So you can see that delta HF is the standard enthalpy change of formation of MX, and I've written an equation to represent this. M solid plus half X2 gas goes to MX. Now the rest of the BornHaber cycle diagram is essentially showing you how you go from M solid and half X2 gas to M plus gas and X minus gas, because the ionic compound MX is made up of positive ions, M plus ions, and X minus ions, and the enthalpy change of lattice formation is essentially the enthalpy change that occurs when 1 mole of an ionic compound is formed from its ions of the element in the gas phase. So the other enthalpy changes that make up this diagram are the enthalpy of atomization of M, where you're forming 1 mole of M gas, the ionization energy of M, where you're converting a mole of M gaseous atoms to M plus ions that are gaseous, the enthalpy of atomization of X, where you're forming 1 mole of gaseous X atoms, and the electron affinity of X, where you're converting 1 mole of gaseous X atoms to 1 mole of gaseous X minus ions. And that completes our BornHaber cycle. As I've mentioned previously, you will be given data to complete this cycle, numerical values, and you'll have to use this to find a missing value. So you're usually asked to find either an enthalpy of lattice formation or an enthalpy of formation of an ionic compound. Now it's also worth mentioning that I've chosen to use this format for drawing BornHaber cycles because the actual figures in a calculation may be positive or negative, but if I use this format, all I simply need to do is substitute them into the diagram. It doesn't matter if they're positive or negative. So we're now going to go through a worked example where we're going to use the following BornHaber cycle and the data below to calculate the standard enthalpy change of lattice formation of sodium chloride. So if you'd like to have a go at this question first, read through the question, pause the video, have a go at it, and then we'll go for the answer. So in this example question, I have to use the following BornHaber cycle and the data below to calculate the standard enthalpy change of lattice formation of sodium chloride. So I'm underlining what I need to find out here. So all I'm going to do is I'm going to take the values that are on the right hand side and put them onto my BornHaber cycle diagram. So the delta HF for NaCl is minus 411 kilojoules per mole. The enthalpy of atomization of sodium is 108.3 kilojoules per mole. The ionization energy of sodium is 500 kilojoules per mole. The atomization of chlorine is 121 kilojoules per mole. And the electron affinity value of chlorine is minus 364. So in this question, we're trying to find out the enthalpy change of lattice formation of sodium chloride. So we're going to use Hess's Law here. And Hess's Law says it doesn't matter if a reaction takes place in one step or a number of steps, the energy change is the same. So if I have delta HF here, which is minus 411, I could go an alternative route to convert Na solid and half Cl2 gas to NaCl. And I've drawn an arrow here in purple right the way around my diagram, which shows an alternative route. So minus 411 is delta HF, and that would be equal to 108.3 plus 500 plus 121 plus minus 364 plus delta H lattice, the enthalpy change of lattice formation of sodium chloride. And that's what I'm trying to find out. So if we want to find out the enthalpy change of lattice formation for sodium chloride, all I need to do is rearrange this equation. So minus 411 minus 108.3 minus 500 minus 121 plus 364, because I need to change the sign here because I'm moving the minus 364 over to the other side, is equal to the enthalpy change of lattice formation. So if I put these numbers into the calculator, the enthalpy change of lattice formation for sodium chloride comes out to be minus 776.3 kilojoules per mole. So here's our first practice question. Read for the question, pause the video, have a go at it, and then we'll go for the answer. So the first thing you have to do to answer this question is you have to draw a Born-Haber cycle diagram. So I've drawn this for potassium bromide. So you can see that I have delta HF, where I have K solid plus half Br2 gas forming KBr, and that has a value of minus 392. I have the atomization enthalpy of potassium here, which is 89. I have the ionization energy of potassium, where I'm going from K gas to K plus, and that's 420. I have the atomization enthalpy of bromine, where I'm forming 1 mole of gaseous bromine atoms, and that is equal to plus 112. And then I have the electron affinity for bromine, where I'm forming 1 mole of Br minus ions, gaseous Br minus ions, and that is equal to minus 342. And then the enthalpy change of lattice formation is what I'm trying to find out. So once again, to work out this missing value, I'm going to take my value for delta HF, which is minus 392, and I'm going to find an alternative route around the diagram to get from K solid plus half BR2 to KBR, and therefore I'm going to have minus 392 equal to 89 plus 420 plus 112 plus minus 342 plus the delta H lattice value, the enthalpy change of lattice formation. Now I don't have to change any signs of these numbers unless I'm going a different direction to the arrows, but here I'm going the same direction as the arrows all the time, so I don't have to change any of these signs. So if I rearrange the equation, I have minus 392 minus 89 minus 420 minus 112 plus 342 equal to the enthalpy change of lattice formation. And if I put these values into the calculator, I get a value equal to minus 671 kilojoules per mole. And this value is, as expected, exothermic, because when you form a lattice, energy is given out. So here's our final practice question. Once again, read for the question, pause the video, have a go at it, and then we'll go for the answer. So the first step in answering this question is to draw out a Born-Haber cycle diagram for barium chloride. Now barium chloride is made from barium, and that's a solid, and chlorine gas. So Ba plus Cl2 makes BaCl2, and the delta HF value here is minus 860. Now I have to convert my barium solid to barium gaseous atoms, so I need atomization, and that has a value of 175 kilojoules per mole. Then I have to convert my gaseous barium atoms to gaseous barium ions, and my value here for ionization energy is first 500, and that's to remove the first electron from barium to make Ba+, but I have to end up with Ba2+, so I need a second ionization energy, which is 1000 kilojoules per mole. I then have to convert Cl2, so chlorine gaseous molecules, to 2 moles of gaseous chlorine atoms. Now the enthalpy of atomization of chlorine is forming 1 mole of chlorine atoms, but I need 2 moles of chlorine atoms. So I have to times the atomization of chlorine value, 121, by 2, because I want to form 2 moles of chlorine atoms. Now I also need 2 moles of Cl- ions. So I need 2 lots of the electron affinity of chlorine. So it's 2 times minus 364. Now to work out my enthalpy change of lattice formation, I'm going to make delta HF equal to the sum of the other enthalpy changes on the diagram. So minus 860 is equal to 175 plus 500 plus 1000 plus 2 lots of 121 plus 2 lots of minus 364 plus the enthalpy change of lattice formation. So this can be simplified as minus 860 is equal to 175 plus 500 plus 1000 plus 242 plus minus 728 plus the enthalpy change of lattice formation. And if I want to find out the enthalpy change of lattice formation, I just simply rearrange this. So the enthalpy change of lattice formation is equal to minus 860, minus 175, minus 500, minus 1000, minus 242, plus 728. And if I put these values into the calculator, I get my value for the enthalpy change of lattice formation, which is equal to minus 2049 kilojoules per mole. So that concludes this video lesson. So after watching this video, you should now understand the processes involved in the formation of simple ionic compounds as described in a Born-Haber cycle, and you should be able to construct BornHaber cycles from given data and be able to use these cycles to find enthalpy values. So that concludes our video. Please check out our YouTube channel, Dr. O Chemistry, and our Twitter site, which contains lots of chemistry information and links, @RadaChemistry.